we'll derive the buckling ordinary differential equation for a beam in the special case where it's bending uniformly about the major x-axis. So here we see on both sides we have a constant externally applied moment, so therefore the beam is going to be in tension all along the bottom flange, assuming it's simply supported, with a uniform bending moment equal to m0. So when the beam becomes unstable, given the top flange is in compression, the beam deflects laterally in the x direction, so into the screen in its elevation view, and it twists about the z-axis. So as discussed, that's known as lateral torsional buckling. So in the deformed state of equilibrium of the beam, we apply the moment curvature relations that we derived earlier. So we have the bending moment about the x dash axis is equal to the bending stiffness, which is the Young's modulus, by the second moment of area of the beam, about x dash, by the second derivative of the vertical deflection in the y direction, with respect to z. So in its deformed state, the beam bends about the x dash axis, and it also bends about the y dash axis. So the other moment curvature relation is the bending stiffness, which is the Young's modulus by the second moment of area about the y dash axis, by the curvature, which is the second derivative of u, where u is the lateral deflection in the x dash direction with respect to z. And the twisting moment about the z dash axis is equal to the torsional stiffness, which we derived earlier when we analysed the beam under a torque, by the rate of twist, which is the derivative of the angle of twist with respect to z, minus the warping stiffness, which is the Young's modulus by the warping constant, by the third derivative of the angle of twist as we move along the z direction. So these are the moments that are developed in a beam when it undergoes lateral torsional buckling. And now we want to relate these to the externally applied moment m0, which is the applied moment about the x-axis. So to do that, we're going to use the directional cosines. So if we construct the matrix, being the transformation matrix, applied to the moment vector, so we only have an externally applied moment about the x-axis, and none about the y and z-axis, and that results in these moments that are developed in the beam when it undergoes lateral torsional buckling. So we have mx dash, my dash, and mz dash. So in the columns, we have the moment about the x-axis, y-axis, and z-axis, and the rows correspond to x dash, y dash, and z dash. So for example, if we consider m0 about the x-axis, and we want to relate this to the developed bending moment about the x dash axis, then the direction cosine between these two moments can be obtained by using the dot product. So that's the cosine of the angle between these two vectors, being phi. And the cosine of the angle between the m0 vector and my dash is cosine pi on 2 plus phi. And in the plan view, noting that z dash is tangent to the lateral deflection curve, then this angle here is minus the rate of change of the lateral deflection as we move along the z-axis. So therefore the cosine of the angle between the moment about the x-axis and the torsional moment about z dash is pi on 2 minus du dz. So as we mentioned, given that we only have an externally applied moment about the x-axis and none about the y and z-axis, then if we multiply this matrix by this vector, the second and third columns don't contribute. And now using our small angle approximation, we will only consider small deformations. So phi is much less than 1. Then cosine of phi is approximately 1. And using trig identities, we know that cosine pi on 2 plus phi is minus sine phi. And using the small angle approximation, sine phi is approximately phi. So we can write this as minus phi. And here we have the cosine of the complementary angle to du dz, which is the same as sine du dz. And the sine of a small angle is equal to that angle. And now if we multiply these out, we get mx dash is m naught, my dash is minus phi by m naught. So noting this should be du dz. So we have mz dash is equal to du dz by m naught. And now we can substitute for these moments in these differential equations. And then subtract them from the left hand side. So with the first equation, we get 0 and minus m naught. And similarly, we get 0 here and plus phi m naught. And here we get 0 on the left hand side and minus du dz m naught. And now let's make a bit of space here. So let's label this equation 1, 2 and 3. And now we differentiate 3 with respect to z. So that gives 0 is the torsional stiffness, or the second derivative of the angle of twist with respect to z, minus the warping stiffness, or the fourth derivative of phi with respect to z, and minus the second derivative of u, being the lateral deflection with respect to z, by m naught. So we'll call this equation 4. And if we multiply 2 by m naught and divide through by the lateral bending stiffness, we get 0 is m naught by the second derivative of u with respect to z plus the angle of twist by m naught squared on the lateral bending stiffness. So that's equation 5. And then adding 4 and 5 effectively eliminates these terms. So what we get is 0 is the torsional stiffness by the second derivative of the angle of twist with respect to z, minus the warping stiffness by the fourth derivative of phi with respect to z. And then these terms cancel, and then we have plus phi by m naught squared on the lateral bending stiffness. And now we can divide through by the warping stiffness and take all these terms to the left hand side. So we get the fourth derivative of phi with respect to z minus the torsional stiffness on the warping stiffness by the second derivative of phi with respect to z, and minus the reciprocal of the warping stiffness by m naught squared on the lateral bending stiffness by the angle of twist, and that's equal to 0. And if you solve this ODE, we'll get an equation of a similar form to that of the buckling of a column. So we get sine of lambda 1 by L is equal to 0, which I'll leave here as an exercise, and I'll give you a few hints. So similar to second order ODEs, we assume a solution of the following form. So the angle of twist is E to a constant by Z, which you differentiate 4 times and substitute in your ODE. And then the boundary conditions you'll apply being no twisting, but free warping at the ends of the beam, which in this case for our beam, so assuming it's simply supported and subjected to externally applied moments, we have no twisting at the supports, so the angle of twist is 0 at z equals 0, and z equals the length of the beam, and we have free warping at the ends, so therefore the second derivative of the angle of twist is equal to 0 at the supports. So the beam can warp at the supports. And recall the condition of free warping was covered when we derived the torsion ODE. So then doing some algebra, you'll come up with this equation, which is satisfied for lambda 1L is a multiple of pi, where n is a positive integer. And taking n equals 1, which gives the critical case, we get lambda 1 is equal to pi on L, and lambda 1 is written compactly as the square root of the square root of alpha squared plus beta minus alpha, where the constants alpha are equal to 1/2 by the torsional stiffness on the warping stiffness, and beta is the square of the externally applied moment on a lateral bending stiffness by the reciprocal of the warping stiffness. So you can use these to check your solution. So here, because we've taken n equals 1, we have the critical buckling moment in this expression. And therefore, if you solve this equation for the critical buckling moment, you'll get m0 critical is the square root of pi squared by the bending stiffness on the length of the beam squared by the torsional stiffness plus pi squared by the warping stiffness on the square of the length of the beam. So when a beam buckles, it buckles laterally and twists and warps. So this is similar to the Euler buckling load, which we had for a column. So recall the critical buckling load for a column is pi squared EI on L squared, and you'd replace this with the effective length based on different restraints applied to the column. And similarly for a beam, based on a different restraints applied to it, you'd replace L with the effective length, where the effective length is going to depend on twisting and rotational restraints.